Okay, let's dive right into this explainer and essentially reverse engineer the Cambridge Physics exam. We're talking specifically about mastering thermal transfer applications by working backwards from success. I want you to imagine something for a second. Imagine if you could see your completed, perfectly graded exam paper before you even start the clock. Like being a time traveler? That is exactly what we are going to do today. Let me paint a picture for you by introducing two typical students you'll find in any exam hall. Over on the left side, we have Alex. Now, Alex is an absolute textbook machine. When faced with a past paper question, let's say syllabus code 0625, regarding a car radiator, Alex just overloads the answer with raw physics facts. We're talking dumping every single equation they've ever memorized onto the page, but completely missing the actual analysis. The result? A painful 1 out of 4 marks. Then, on the right side of the hall, we have Sam. Sam's problem is different. Sam rushes. Sam sees the command word convection, gets way too excited, totally misses the specific requirements of the prompt, and just writes a really generic answer about how hot air rises. And again, you guessed it, 1 out of 4 marks. Today, we are going completely hands-on to fix both of these fatal flaws. We're going to show you exactly what the senior examiners are desperately looking for, and we're going to transform those red pen marks into green check marks.
So the crucial point you absolutely need to realize first is that thermal energy transfer applications, things like your kitchen pans, convection heating in rooms, wood fires, and those tricky car radiators, they account for a massive 15% of your total exam marks. That is not just some minor footnote in the syllabus. That 15% is effectively the difference between two entire grade boundaries. If you're sitting at a B and you want an A, or you're at an A and you're gunning for that A star, this 15% is literally your golden ticket. You see, the Cambridge examiners love, and I mean love, testing these concepts because they beautifully bridge the gap between theoretical textbook physics and actual real-world engineering. Think about it. When you fry an egg in a kitchen pan, you aren't just making breakfast, you are witnessing conduction in a solid metallic lattice. When you heat a room with a radiator, you are actively manipulating fluid density to create convection currents. And when a car engine relies on its radiator, well, that's just a brilliant symphony of conduction, convection, and radiation, all working perfectly together to prevent a catastrophic engine meltdown. Mastering this 15% means you actually understand the very fabric of how energy moves through our universe. Whether you're taking 0625, 0651, 0652, 5054, or even setting foundations for A-Level 9702. All right, here is our visual syllabus for today's explainer. We'll be heading, number 1, the 15% challenge. Number 2, connecting core principles. Number 3, the technical methodology. Number 4, deconstruct, solve, evaluate. And finally, number 5, top examiner warnings. Let's get right into it.
Section 1, the 15% challenge.
Let's start with why students actually find this specific 15% so incredibly difficult. It boils down to applying known concepts to completely unfamiliar contexts. This is exactly where our friend Alex went terribly wrong. You see, Alex memorized the textbook definition of conduction perfectly, but when the exam threw a curveball and asked why a specific type of kitchen pan, one with a copper base but a plastic handle, is optimal for heating soup, Alex completely froze. The challenge here isn't the underlying physics. The challenge is the context. The Cambridge examiners intentionally design these questions around scenarios you have never explicitly studied in class. They don't want to know if you can act like a parrot and squawk back a definition. They want to know if you can use physics as a real tool to solve a mystery. The assessment objectives here target highly distinct cognitive domains. You must shift from simply memorizing facts to actively analyzing them in real-world scenarios. We're talking moving from pure knowledge right into heavy application. This is exactly where top-tier students rely on what we call the PEAL framework. That stands for point, evidence, explanation, link. It's how you ensure you hit every single command word. Instead of Sam's generic, the heat goes up, a true PEAL answer looks like this. Point, the fluid becomes less dense. Evidence, the thermal energy increases the kinetic energy, causing the particles to spread further apart. Explanation, the less dense fluid rises above the denser, cooler fluid. Link, this continuous cycle creates a convection current that heats the entire room. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving right along to Section 2, connecting core principles.
Okay, so the theoretical architecture of these applications rests heavily on precise definitions and causal relationships. Let's think back to Sam for a second. Sam rushed and confidently wrote that heat rises. Listen closely. In physics, heat doesn't rise. Hot, less dense fluids rise. That distinction right there is a causal relationship, and getting that phrasing right is literally the difference between a 0 and a full mark. You absolutely must understand that thermal energy transfer is always driven by a temperature difference, and it will continuously flow from a region of higher temperature to a region of lower temperature until thermal equilibrium is reached. But here is the real secret sauce on this slide. Look at that third slice, cross-topic connections. Principal examiner reports constantly highlight that candidates who reference cross-topic connections achieve significantly higher marks. It's your secret weapon. Let's take the car radiator example again. A standard average student will only talk about thermal transfer, but an exceptional A-star student, they will connect the car radiator's large surface area to the rate of radiation. They might even link it back to the specific heat capacity of the actual coolant fluid used inside the radiator. By actively bringing in a topic from a completely different part of your syllabus, you are waving a massive flag to the examiner that says, hey, I don't just memorize isolated chapters. I understand physics as one unified, interconnected system. That is how you transform a basic answer into an examiner's dream.
Section 3, the technical methodology. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, welcome back. This is where we start doing the heavy lifting. This is where we turn raw knowledge into a professional, high-scoring exam script. When you sit down in that exam hall, you aren't just a stressed-out student anymore. You are a cold, calculating analyst being presented with a data set. Whether it's a wood-burning fire or a convection heater, you cannot rely on a sudden burst of inspiration. You need a rock-solid system. So let's run an interactive workshop right now, using this 5-step procedural framework. This is Challenge 1, the data scan. I want you to imagine a complex physics data table right in front of you. You've got 60 seconds on the clock. Step 1 is identifying the key elements. You scan it. What's the hot object? What's the cold object? What's the medium transferring the energy? Step 2, apply relevant principles. If the medium is a solid lattice, boom, that's conduction. If it's a fluid, it's convection. If it's a vacuum, you're dealing with radiation. Step 3 is executing your analysis with incredibly clear working. Examiners desperately want to award you marks for your process. Step 4 is verifying the results, and Step 5 is presenting it in that perfect peel format. This sequence guarantees you don't miss a thing. And this brings us to Challenge 2 in our workshop, Find the Flaw. This slide brilliantly illustrates how you must handle comparative analysis, which means identifying both similarities and differences using comparative connectives and backing it all up with data. Let's play a game. I'm going to read you a flawed sample paragraph, and I want you to mentally flag the sentence that loses the mark. Ready? The black surface of the car radiator is better because dark colors attract heat, making the engine cool down faster. Did you catch it? The fatal error losing the mark is the phrase attract heat. Colors absolutely do not attract heat. It's not a magnet. Black surfaces are superior emitters and superior absorbers of infrared radiation. When you compare materials, like evaluating the thermal conductivity of 4 unknown metals for a kitchen pan, you have to extract the exact trend. You need high thermal transfer, but also structural integrity under heat. Your comparative analysis and your specific terminology have to be absolutely flawless.
Section 4, deconstruct, solve, evaluate.
Now we are transitioning into the ultimate problem-solving engine. Let's do Challenge 3, speed writing. You've got 30 seconds to mentally draft a perfect PEL paragraph explaining why the heating element in a convection room heater is placed near the floor. Let's build it together using deconstruct, solve, evaluate. First, we deconstruct. Point, placing it at the bottom allows for efficient heating of the entire room. Evidence, the air immediately near the heating element gains thermal energy and expands. Explanation, this expansion decreases the air's density, causing that specific pocket of air to rise, which displaces the cooler, denser air downwards so it can be heated in turn. Link, this continuous cycle establishes a stable convection current. Boom, that's a top-tier answer. Then you solve, meaning you systematically apply your formulas for any math portions, keeping your working incredibly neat. Then, critically, you evaluate. You must check your final output for reasonableness. Look, if you're doing a calculation for a coal fire heating a standard boiler system, and your math suggests the water just reached 50,000 degrees Celsius, your evaluation step should trigger massive alarm bells in your head. Water would have vaporized into steam ages ago. Checking for reasonableness prevents these silly, rushed arithmetic errors from destroying your hard-earned method marks. Section 5, top examiner warnings. Let's look at the actual traps people fall into.
We have literally scoured years of Cambridge examiner feedback. And I'll tell you, this same agonizing mistakes appear year after year. These are not just helpful suggestions. These are the actual, documented reasons why students who know their physics inside and out still end up with C's instead of A's. This direct examiner alert proves a fundamental rule. How you solve the problem, your clear notation, your methodology, is exactly what guarantees your method marks. I cannot stress this enough. If you type a massive calculation into your calculator, hit equals, get a number, and just quickly scribble that single number on the answer line, you are gambling your entire grade. If your finger slipped and you pushed a wrong button by accident, you get a 0, nothing. But if you write down the formula, substitute the numbers clearly on the page, and then make a calculator error, the examiner will see your logic. They will award you the method marks. Your process is honestly often worth more than your final destination. You need to treat your exam paper like a legal document, where you have to prove your case beyond a reasonable doubt, step by step.
So let's lock in the final system. Never, ever make these top 3 mistakes. Number 1, forgetting proper format. This means missing your units. If your answer is 42, is it 42 joules, 42 watts, 42 degrees Celsius? A naked number in physics is completely meaningless. Number 2, failing to check presentation. Look, if your handwriting is so messy from rushing that your number 5 looks like a letter S, the examiners simply cannot give you the mark. They won't guess. Number 3, the absolute most common, heartbreaking error of them all, providing non-specific answers. If the question specifically asks about a copper kitchen pan, your answer must specifically mention the free electrons in the metallic lattice of the copper transferring kinetic energy. If you just write, the pan conducts heat, you get absolutely nothing. You have to tailor your physics knowledge strictly to the exact scenario on the page. Now listen closely. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. As you prepare for your upcoming exam, you really need to shift your mindset. Stop focusing just on finding the right answer and start focusing on mastering the process. By mastering command word decoding, applying the Peel framework relentlessly, and using our time management matrix and the deconstruct solve evaluate method, those intimidating thermal transfer questions are going to become your highest scoring section. So, when you open your next exam paper, are you going to see a list of terrifying unknowns, or are you going to see the underlying physics just waiting to be decoded? The blueprint is in your hands now. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Also, drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.